Another important aspect that I wanted to cover in today's class was also this qualitative discussion on the influence of inequality and equality constant on optimization problem. And this is something that I alluded in the first lecture, set of lectures that we had, where I said that equality constraints are a little bit stricter and severe than inequality constraint. Let's use this graphical approach to see how does equality constraint and inequality constraints differ and how they affect the overall solution space of the problem. Now, all of this discussion is qualitative just for understanding purposes, but conceptually you should be able to see that equality constraints are severe compared to inequality constraints. So again, we have essentially x1 and x2, we have a contour plot for an objective function, and I'm not specifying what is the exact nature or exact function, but these are essentially, essentially a contour plot for an objective function, okay? And if we have similar to the previous problem, 4 inequality constraints which define this region, let's call this region as, A, B, C, and what we do, A, B, C, and D. And how we can arrive at this, we saw that previously we used 4 inequality constraint that lead to a slightly different shape, and this one is leading to a different shape, but we can use 4 different, where this one is probably G2, this one is probably G1, right? And similarly this one is G3, and similarly this one is G4, right? This is G4, and using those 4 inequality constraints, we got this feasible region. So anything inside this box is essentially, feasible region. Okay, and why? Because the dashed are out, the hashed out region is the out on this side. So anything just inside this box or this region A, B, C, D is essentially a feasible region. Okay, so that's qualitative aspect that we are coming, that you have a region which is feasible defined by these 4 inequality constraints that we have. Now let's see how does an equality constraint offer. So what we have now, at least visually, we have one objective function, okay, which is defined by this set of contours, and we have 4 inequality constraints which are defined by this shaded region. And on top of that, what happens if I add one more equality constraint? Okay, and let me revise and let me put that what we are doing here is we have one objective function and 4 inequality constraint function. Okay, and that resulted in this plot that we have. So what I want to do is, what happens if I add one more equality constraint on top of this 4 already defined inequality constraint? Now there might be 2 possibilities that can happen. One possibility is that the line that I defined again, and again I will use basically a simple line or straight line equation to explain this concept, that if I use a line which represents this equality constraint, right, that line can either lie inside the feasible region or it can lie outside the feasible region. Okay, so let's see what happens in both the scenarios to understand the imposition that equality constraints bring to the overall optimization problem. Okay, and again, these are inequality constraint line, and this is the feasible region. Okay, so here is the case 1, right, where we have added a 5th constraint, and this one is an equality constraint, and this might be equation of line which is defined by a1 x1 plus b x2 is equal to this is equal to 0. So that's what this line is defined. Okay, so if I choose suitable coefficient a and b, I might have represent this line. And remember, since this is an equality constraint, what does it do? The overall solution now is forced to lie on this line itself. This is never not a less than or greater than equal to sign. So we are not deciding the regions which are on left and right of this region just because we have equality constraint. Now we are forced to have the solution lie exactly on the line. So you can see, when in the case where we have inequality constraint, at least what we are doing is, if I take this inequality constraint, then we know that this region is infeasible, but this side of the line is feasible, right? So it's a little bit more flexible. It gives me some room to play with. Whereas if I have the equality constraint, now I cannot choose this region or this region. We are forced to lie on this line. So only solution or only points which lie on this line are going to be feasible. Okay. So if we come to this case where on top of these 4 constraints, inequality constraint that we have, we add an additional constraint which is defined by this, and which is case 1, which is lying outside the feasible region. What is the overall solution for this problem? It turns out, this line is not in the feasible region defined by previously to 4 inequality, and this is additional constraint that we are adding. In this case, we will not have any feasible solution, and there will be no solution to this optimization problem whatsoever. And that shows the severity of how, first, that we are forced to only lie on the line, and the second, this line might not be in the feasible region defined by the inequality, and that's why we might land up with the case where we do not have any feasible solution, or we do not have any optimal solution to this overall problem. So there is not even a single point that is feasible, and therefore we cannot have any optimal point whatsoever. So that's case 1. But let's also look into another case where we might have a line which also lies inside the feasible region that is defined by the 4 inequality constraint functions that we have, right? So what we'll do is we will try to draw a line in case 2 which basically is inside the feasible region, or which is inside this region. So let's see what happens there. Okay, and again, this is an inequality constraint, and this leads to infeasible solution, and there is no feasible solution in this case, so we will not have any optimal solution whatsoever. So now let's look into case 2, where the case 2 represents an equality constraint, which is the 5th constraint that we are adding on this problem. But in this case, that equality constraint will be passing through the feasible region that has been defined by the inequality constraints. So if that is the case, I can have this line, which is probably represented by some unique combination of this coefficient a and b equal to 0. So if I choose some suitable coefficient a and b 0, we might land up in this case where the line is passing through the feasible region. So now this is a case 2 where we have an equality constraint. Again, this is the 5th constraint that we are defining, and that is basically passing through. Now, what is the effect of this constraint on the original overall optimization problem? Now, the first thing that I want you to notice is once we add this 5th constraint, which is passing through the feasible line, right? Initially, we had this whole space which is defined by A, B, C, and D right here, which was feasible. And if I choose any point here, here, any point here, here, or so on, all of these points was feasible. Now, since we added this 5th constraint, it turns out these points are no longer feasible solution for this. Now, for us to satisfy the feasibility criteria, what we need to do is not only we have to look into the region which is inside the ABCD region, which is defined by the inequality constraint, but the solution point now has to lie on this line. So now what we do is for feasibility, the point has to be in ABCD region, and on the top of that, it has to lie on the line. So the points that I am drawing right now on the top of the lines are the only feasible, although there are infinitely many solutions here, but you can see that the overall solution space that was defined by A, B, C, D has now shrinked considerably, and all the feasibility is now focused on a single straight line that passes through that region. So in that sense, first takeaway is from this large space of feasible region, we are now restricted to a space of feasible solutions that are only on that line. And that is the effect of an equality constraint. It essentially shrinks down the space of possibilities, the space of feasible solution points that we have. That's one aspect. The second aspect that I want to qualitatively describe, that if this line was not here, right, in the previous problem that we talked, in that problem, if the contour value of the objective function, which are defined by this contour, if they are decreasing in this direction, right, then we will be moving on and we will see that there will be a contour that passes through point A and the optimal solution lies here. So in the first problem where we only had the 4 inequality constraint, the optimal solution was here. Now, we added this fifth constraint, the optimal solution has to lie on this line. So no longer this one is active, or this solution is the optimal solution. By imposition of this line, the solution or the location of the optimal solution has changed. So in other words, we discussed the concept of active constraint in the previous class. This line is acting as an active constraint because it is now going to change the location of the optimal solution if it was not present. If it was not present, the optimal solution was here, but now it is present and it is changing the location of this, and the solution has to lie on this line. Okay, so it's an active constraint. That's another important aspect that you have to understand. By adding this fifth, constraint, now the solution has to lie. The question is where that solution is. Now, same idea is same, that we will keep moving this contour line, keep going, and we will see that if I draw a line like this, right, again, that line will be essentially parallel to this line and parallel to this line, but that line will be passing through this point here in this direction. So this will be essentially in the hashed direction that contour line will be passing through, and that will be intersecting with this point. Let's call this point as point E, and that point is now the optimal solution. Okay, and no longer this point is an optimal solution to the problem. So by adding, two things has happened. Again, the space of feasibility has reduced and also the location of the optimal point has changed. And in that sense, this equality constraint is an active constraint and it's changing the location of the optimal points. So these are two important things that I wanted to convey, the activity or inactivity of the constraint and the severity of the constraint imposed, or the differences in the quality of constraint that is being imposed by inequality constraints and equality constraint. And I want to highlight that typically, in most of the cases, equality constraints are a little bit more severe, whereas in inequality constraints, you have a lot of space to still play with. With that, we'll stop and we will come back again with a new set of lectures where we will be dealing with other salient aspect of optimization, still using graphical approach. With that, thank you.